Here's a question for you. How can the heart increase the force of contraction? And in fact, in thinking about this, kind of put yourself in the position of the heart. You know, the heart is working very, very hard every single day to beat. And now if you're the heart, let's say this is you, and you've got to figure this out. You're working very diligently, and now the heart is being asked to do even more. So what's the answer? How do you actually increase the force of contraction? Well, you know that there's one form of energy that's being converted to another. So that's chemical energy, and we think of the molecule ATP. When I say chemical energy, that's the one I'm kind of thinking about, is being converted to mechanical or kinetic energy. I'm going to write mechanical energy. And this process of going from chemical energy to mechanical energy is creating this kind of force of contraction. This is how you're getting the force of contraction. And there is a specific protein that's actually allowing you to even do this, right? This protein is going to look a little bit like this. And this is our myosin head. In fact, not even a whole protein. This is a part of a protein. So the myosin head is what is actually allowing you to convert chemical energy into mechanical energy. And so the question you can actually rephrase as, how do you get more myosin heads working? That's really kind of the answer to this, right? If we wanted more force, you need more myosin heads working. So if you have, let's say, let's say you have 100 myosin heads working, then how do you get 200? Or if you have 200, how do you get 500? So in any case, how do you get more going? And really to answer this, then we have to figure out what it is that myosin heads need to do their job. So let's start with two key criteria, right? So two key things that we know they need. One is they need to be nearby actin. So we know that they need to be working and nearby another protein called actin. So if they're far away from actin, this whole thing's not going to work. They're not going to be able to do their job. And remember that there's this issue of polarity. And all I mean by polarity is that actin actually has a certain direction. So not only do they have to be close to actin, they have to be close to the actin going in the right direction. And a second thing is that they actually need calcium, right? Calcium needs to bind troponin C. And why is that? Well, remember troponin C, I'm going to write trop C, but that's troponin C. Troponin C is actually going to move tropomyosin out of the way. So that's just to kind of remind you of what it does. And when tropomyosin is moved out of the way, then actin is free to bind myosin. So these are the two important kind of things we have to consider, right? We need to make sure that our myosin is nearby actin and that calcium is binding troponin C. Let me make a little bit of space. I'm going to pull up something that I drew earlier. And I thought we could actually split this talk into two parts, because another issue is kind of, are we talking about end of systole or end of diastole, or what time point are we talking about exactly? And of course, it's always nice to kind of label this stuff. So let's talk about end of diastole on this side, and on the other side, I'll squeeze in end of systole. So this will be end of systole. So these are the two time points that I think are important to kind of discuss separately. In terms of our two criteria, which of these are going to meet the criteria? Well, let's go one at a time. Nearby actin. So which of these myosin heads is nearby an actin that it needs to be nearby? Well, those three for sure. And then these five are near the correct polarity as well, as are these five and these three. But now I've actually not circled a couple of things here, right? I ignored circling these two and these two. And the reason is because they are actually nearby actin of the wrong polarity. And I actually even drew in the arrowheads on the actin so you could see what I mean, right? They're nearby actin going in the wrong direction as opposed to what they would need to bind to. So I've got a total of how many blue circled myosin heads? We have 16, right? So remember, criteria 2 is about calcium. And now let me throw up a random number. Let's throw up the number 10. Let's say there are 10 calcium ions kind of floating around. Actually, let me make it a bigger number just to illustrate another point. Let's say 20. 20 calcium ions floating around. And now let's say that they are going to have to bind troponin C. Well, troponin C, let's say, only binds about 50% of the calciums that are around. So only 50% bind troponin C. So what are you going to get? You get 50% times 20. You have 10 calciums that are going to bind. And actually, let me go ahead and create a dividing line here. You have 10 calciums that are going to bind. So let me just kind of sprinkle some calciums, 10 of them, in here, and let's see what happens. So let's go 1, 2, let's go 3, let's go 4, 5, 6, 7, 8, 9, and 10. So 10 calciums there. And now the question is, how many myosins are working? So I'm going to just circle, or with little red arrows, I'm going to point to the myosin heads that are working, that satisfy our 2 criteria. So far we've got a couple there, and then we've got this guy here, we've got this guy here, we've got one here, and I think that might, oh, yep, we've got one here. So we've got a total of 7 that are working. So let me actually just write that. 7 out of 20 myosin heads are working. So that's not too bad. That's not quite even 50%, but let's just kind of tuck that away. And let's say that, and we know this, we actually redo this with a strategy in mind. So the heart actually wants something better than 7, and we know that the main strategy, and we've talked about this, but really not in this context, the main strategy for getting more myosin heads working is going to be called stretch. So this is kind of, if you were to think of one word answer to our initial question, how do you get more myosin heads working? You basically stretch. At least if you're in end of diastole, that is the answer, right? We know that's kind of the key idea. So let's now bring up a stretched out version of this and see what would happen. So in a stretched out version, you have, let's say again, 20 calciums here. And instead of binding 50% of them to troponin C, we know more of them are going to want to bind, because that's one of the keys with stretching. You'll recall that now troponin C is going to really want to bind to calcium, so more of it binds. And that's one of the interesting properties of troponin C, is that it can actually change its affinity for calcium. So 15 calciums are going to bind now, and that's up from just 10 earlier. And just like before, I'm going to circle the blue myosin heads that are near actin of the right polarity. So far we've got 5, 10, and basically all of them, right? All of them are basically near actin of the right polarity. So unlike before, where some were and some weren't gonna be near actin that they needed to be near, here all of them are. And then I can draw calcium kind of binding randomly, and I'm going to draw it binding all different parts of actin. Now you might think, well, why is it binding all the way to the left over there? There's no myosin over there. But remember, calcium will just bind troponin C wherever it darn well feels like. So it'll bind anywhere. And even if myosin's not there, it'll still bind there. So we've got, let's make sure I've got the correct, I think I've got 3 more to go. 1, 2, 3. So now we've got a total of, let's say, I'm going to draw red arrows next to the ones that are working. So we've got 1 myosin here, 1 here, 1 here, 1 here, 1 here, here. Basically, anywhere a calcium is bound, I've got a myosin head working. So now I've got a total of 9 out of 20. So this has actually gone up considerably, right? 9 out of 20 are bound. So this is actually really, really nice to see. We've actually, using stretch, we were able to recruit a couple more myosin heads to work. And again, these numbers I'm just throwing out, so I don't want you to be wedded to the numbers, but I want you to get the concept that stretch actually helped us increase the amount of myosin that was converting chemical energy to mechanical force. Now, this is all happening in end diastole, and that's all well and good. But what about end systole? What's happening there? Well, here you can see that basically at the end of systole, the 2 myosin actin drawings that I have here look very similar, pretty much the same. So at the end of systole, when everything is kind of contracted down, the idea of stretch is going to be less relevant here, right? I mean, that doesn't matter. So we really need to think of a new strategy if we want to get more myosin heads working. And what is that strategy going to be? Well, let's start with our first scenario, and I'll call these top two scenario A's and these bottom two scenario B's. So let's go to scenario A for the end systole. Let's start with kind of circling which ones have myosin heads that are capable of working. So I've got 1 here and 5 here. And you basically see how this is kind of going. I've got 5 here and 1 here. And that's because there's so much blockage happening from this whole chunk right here. Let me draw it in a different color. This whole chunk is basically blocking, and this whole chunk is basically blocking because they're the wrong polarity. Now with criteria 2, we said you need some calcium binding. So what's going to happen there? Well, let's use the same numbers just to keep it really simple. So let's say 20 calciums and let's say 50% bind troponin C. Well, that gives me the same number as before. We're going to get a total of 10, right? So I've got 10 calciums to play with. And I'm going to sprinkle those calciums around. I'm going to put maybe 1 here and 1 here, 3, let's go 4, 5, 6, 7, let's go 8, 9, and 10. So how many actually are going to be working? How many myosin heads are working? Here we got 1 here, and then of course these don't work, right? The ones in the middle here. Let me just circle them. These guys are blocked, both sides. So still at just 1. And then I've got 1 here, he's working. And then I've got 1 here, he's working. Now I want to point out, I've got calcium here and here, but I didn't put an arrow next to those guys because, again, those myosin heads are near actin, but that calcium is actually binding not the nearby actin, it's actually binding to the far actin on the other side. So again, those myosin heads will not be working. So I have a total of 3, only a total of 3. So that's not too hot, right? That's not too great. And now, the strategy the heart uses in end systole is not stretch, but increased calcium. So if you just increase the amount of calcium, then you can actually get a much better outcome. And this is the key idea and the key strategy that it uses. So let's see how it plays out. If you just increase the amount of calcium, I'm going to double it to 40. 40 calciums. This is an incredible number of calciums, right? And let's say that 50%, I'm going to keep that number the same, bind troponin C. So that number is about the same. So that leaves me with 20 calciums, right? 20 calciums. And I can put those 20 anywhere. So I'm going to sprinkle them around. Just 1, 2, 3, 4, 5. I have so many to kind of bind. I've got to just bind everywhere. And just see where this all goes. Make sure I get 20 out here. And let's do something like that. So that's 20 calciums. And now let's figure out what we have. So we have the same as before. These are the myosin heads that are going to be near an actin of the right polarity. So those are the only ones that from the get-go we know could potentially work. And these other ones we know are going to be blocked by the actin of the wrong polarity. So that's an easy way to kind of get started. And then we just have to kind of count things up. And so let's see what we get. I really didn't plan this. I'm just kind of seeing what I get based on random luck. So I've got 1, 2, 3, 4. And then I've got on this side 5, 6, and 7, 8. So I've pointed arrows to the ones that I think make sense. And you can double check that to make sure. Again, you're just looking for a blue circled myosin with a calcium on the nearby actin. And that sounds like a mouthful, but I think I got all that out correctly. So I've got 8 out of 20. So 8 out of 20 is definitely better than what we had earlier, right? So our strategy has worked. We went from 3 to 8, and in diastole went from 7 to 9. So we're definitely seeing improvements. Now, these are the key strategies, and I just want to remind you that it goes back to just doing whatever you can to getting the most myosins at work.